Alright, this is the explanation video for problem set 14. Problem 1 is giving us a parametric equation where x is equal to a cosine theta plus cosine n theta, and our y is equal to a sine theta plus sine n theta. And these are representing, a is representing the distance from the sun, and n is representing times the moon orbits the planet for every one revolution. And it's asking us to find the specific values of a equal 4 as a fixed position and n equaling 3 through 5 as a variable, and to make a conjecture based upon our findings. So what I found was, when I graphed this, that our A looked like it only had one loop, and at B there were contradicting, let's say, crests here, and so I found that there's probably no loops when it is even, and C is equal to 3 loops. So I said when n is odd, the amount of loops is equal to n minus 2, which would make sense because n equals 3 has 1 loop, and n equals 5 has 3 loops. And then when n is even, it does not loop. Moving on to problem number 2, we are given r equals 1 plus c sine theta, and we are supposed to identify how when we change C, how the shape changes. So I said when C is positive and C is greater than 1, we get an increasingly larger, lumicon in the positive y direction. That's where it's increasing in magnitude towards. And when C is negative and C is less than -1, we get the same behavior as it was when it was even, but it's increasing in both size and length towards the negative y direction. And when C is 0, we get a circle about the origin of 0, because we do not have a sign here that will make that go away. We just get r equals 1. And when C is less than -1 and less than 1, so in between that range of -1 and 1 of numbers, we get like an indent, similar to what we see at problem 3, but not quite as pronounced. But it does not actually get that second loop around. It just gets a smaller, larger indent towards the bounds. Moving on, question number 3. It's asking us, giving us a cardioid, r equals 8 plus 8 sine theta, where r is measured in meters, and the microphone is at the pole. And they want to know the area of the stage with the optimal pickup range of the microphone. So we were given the f of theta, which is r equals 8 plus 8 sine of theta, and we're given that is 4 meters away from the stage. So that is our r equals sine theta equals 4, and solving for r, we get 4 over sine theta, which is our g of theta. We can then plug these in by substituting one of the r's and solving for theta. And when we solve for theta, it's a quadratic equation, so we get 2 answers, and those will be our bounds. So our lower bound will be 0.374373, and then our upper bound will be 2.76685. And when we plug this into our equation of the integral of the area bounded by a specific 2 functions here, I plug in our g of theta and our f of theta squared each, with relation to d of theta and our upper bounds and lower bounds taken to the 1/2, and I got that r is equal to 204.16, and that is the optimal area in which they will have the microphone pickup. So that is that. Alright.